In this video, I am focused on the kinematic equations of motion. This is the fourth of 7 videos in my Unit 2, titled Kinematics. If you want to practice what was covered in this video, then check out the video description. You can find a link to my worksheet 2.04, as well as video answers for each problem. Here are the 3 kinematic equations. They are all related to accelerated motion, and they are likely included on your class formula sheet. Each of them contain a different combination of the 6 variables listed in the box to the right, so determining which equation to use will be related to the problem's given information and also what you are solving for. I think the first step of using the kinematic equations is establishing the connected variables in a vertical list. Here we are organizing a problem's given information, determining positive versus negative for vector quantities, and determining which variable to solve for. Knowing the standard units of measure for each variable will help you construct the list properly and determine if any unit conversions are necessary. I think one of the challenging parts of using the equations is when the given information is not presented as the exact number to plug in. Here are 4 written statements. Each of them are hinting towards a specific kinematic variable, and each of them are hinting towards a specific quantity to plug in for that variable. Let's start with the blue statement. We have a ball released from rest. When the ball is released, that is likely at the beginning of the problem, and to state from rest means that the ball was not moving at that moment in time. So this is hinting towards the initial velocity of the ball, v subscript 0, and the quantity would be 0 meters per second. Next, a car comes to a stop. Well, the car coming to a stop would likely be at the end of the problem, and when it comes to a stop, that means it is not moving at that time. So this would be hinting towards the later velocity variable v, and we would also plug in a quantity of 0 meters per second. Next, a train moves for 2 minutes. This is clearly a time, but remember that we want to use the standard units of measure for each of the kinematic variables, and time should be measured in seconds. So for variable t, we would want to plug in 120 seconds, which is 2 minutes converted to seconds. Lastly, an object moves 30 meters. Note that the kinematic equations do not have distance or displacement represented. They contain starting and ending position. So we are being given information for those variables, and as long as the quantities are 30 meters apart, they would be showing that the object moved 30 meters. It is probably best to start at 0 meters and end at 30 meters, but a student would not be wrong to start at 5 meters and end at 35 meters. Let's look at an example. Here we have a car that begins at rest 24 meters in front of a stoplight. When the light turns green, the car accelerates forward at a rate of 3 meters per second squared. And the question is, how fast will the car be traveling when it passes under the light? We'll observe that we have a lot of information for motion variables here. We are also solving for a motion variable, so I think we need to use the kinematic equations. And as mentioned, we should begin with the vertical list of variables. So let's pick out what we know. The first thing I see is that the car accelerates forward at a rate of 3 meters per second squared. I'll assume that the car moving to the right is moving in the positive direction, so I'll use positive 3 meters per second squared next to the acceleration variable. Next, I see that the car begins at rest. This is at the start of the problem. The car is not moving at this time, so its initial velocity is 0 meters per second. For the car to be 24 meters in front of the light, I'll say that the car starts at a position of 0 meters and ends at a position of 24 meters. As long as you plug in numbers here that are 24 meters different, you'll be okay with the answer to this question. For this problem, we are solving for how fast the car will be moving. That would indicate the velocity when it goes under the light or at the end of the problem, and therefore I'll put a question mark next to the velocity variable. So here is the list of what we know and also what we're solving for. Something I'll point out is the time variable. It is blank. That means we don't have information for it, and we are also not solving for it. So for this particular problem, who cares about time? As I look over the kinematic equation options, I am focused on the time variable because I don't care about it, and I would likely want to select the equation that doesn't have time represented. That would mean I'm using only things that I know and what I'm solving for. The third kinematic equation stands out. It contains all the variables we need, and now I'll just want to plug in the information from the list and perform the algebra to solve for the velocity variable. The last step of that would be taking a square root, since velocity is squared in this equation. That will kick out 2 answers, both positive and negative 12. So I want to consider which of those is the best option. This car was moving to the right. It was never moving to the left, so this was always moving in the positive direction, and therefore I would select positive 12 as the correct answer for this problem. Note that one of the other kinematic equations has the time variable squared, so you might be in a similar spot when solving for time, but time cannot be negative, so you always want to choose the positive answer for time. If you found this video helpful, then please consider hitting the like button and subscribing to my channel. You will help me reach more students. For more content videos, tutoring information, practice materials, and live review sessions, check out my website or follow me on my social media platforms.